Our text tells us that pendulum motion exhibits simple harmonic motion, that even though pendulum motion is not a simple harmonic motion, it can be viewed as such. Why? Because simple pendulum motion exhibits several qualities similar to other simple harmonic motions. Motion made by a spring mass system is a proper example. Both simple pendulums and spring masses have forces that can be calculated with nearly identical expressions. This is because both systems are dependent upon a similar force, a linear restoring force. On top of that, they are both measured using Cartesian coordinates. Of course, it's important to point out that there are different types of pendulum motion, and while simple pendulum motion does closely resemble a spring mass system mathematically, the same cannot be said about physical pendulum motion. Because of their size, physical pendulums have a different center of gravity. This means that the derivations used to find frequency for physical pendulums require a couple more variables than are necessary for simple pendulums and spring mass systems. For our experiment, I drove to my local park and videotaped myself swinging on a swing set using a ladder for camera height, a 4-foot level for reference, and the video camera on my phone. After getting 3 good runs at different amplitudes, we plugged it all into video analysis. Video analysis provided us with some great stuff. After plotting some points, setting our origin, and adjusting the scale, it was as easy as ever to read the info provided. The position graph proved to be the most useful aspect. Using it, we were able to determine the amplitude in meters of each run. Doing so would allow the three of us to compare runs with one another. Our theory was that amplitude had nothing to do with the frequency of our makeshift pendulum system. At this point, it is important to note the amplitude of each of our runs and how we obtained said amplitudes. For our slow run, we obtained an amplitude of 0.8 meters. For our medium run, we received an amplitude of 1.4 meters. And for our fast run, the group got an amplitude of 1.6 meters. These values were obtained by observing the local maxima and minima of each position graph. From there, the three of us got to testing our theory that amplitude had little to do with frequency. To do that, we would first need to find the frequency of each pendulum system we'd created. Thankfully, this turned out to be fairly simple. Using video analysis to crop each video to display one singular oscillation, we were able to watch the time on each video to an accuracy of 1 second. For each run, we found period to be about 2 seconds. As period and frequency are inversely proportional, we were able to calculate the frequency of each run by placing 1 over period. Each run had an approximate frequency of 0.33 Hz. Once we had the frequency for each run, the three of us got to wondering, what should the frequency actually be? After realizing we'd forgotten a crucial step, I ran back to the park with a tape measure and took one last measurement. I needed to know the length of the chain I'd swung from. Upon my return, the three of us resumed our Discord meeting, where Casey would set to unraveling our predicted values. Using a length of 1.602 meters, a gravitational constant of 9.81 meters per second squared, and our handy-dandy frequency formula, she was able to determine two values, a predicted period of 2.5404 seconds and a predicted frequency of 0.394 Hz. We noticed several things right away. All the measurements obtained by video analysis regarding period were within a singular second of one another. This was a good indicator that our theory was correct. Another note we might make is that the formula for frequency had no variable for mass or inertia, which, once again, indicated our theory was correct. One last thing we'd notice is that our discrepancy was approximately 16%. We weren't exactly sure how to feel about that. Our experiment had somewhat proved that amplitude had little to do with frequency, but we still didn't understand why, though we had formed a couple theories. After taking a look at a couple free body diagrams online, we determined that there were three main forces most usually in play when a simple pendulum system came up. There was always a tension, always a weight, and for simple pendulum motion, there was always a tangential restoring force. Using Newton's second law, we can prove that weight is equal to tension in this scenario, and since I know my weight to be 146 kilograms, we also knew our tension to be 146 kilograms. From there, a still motion of my body at local maxima and a protractor are all that we needed to determine the angle necessary for our calculations. 30 degrees for our slow run. All that was left was to multiply our findings by setting the restoring force equal to weight multiplied by the sine of 30 degrees. The tangential restoring force was determined to be 73.03 newtons. What's more important than that value, however, was a revelation we'd had only by viewing the free body diagram we'd crafted. After looking long and hard at the picture, it clicked. If weight and tension offset each other, they're somewhat obsolete in regard to frequency. So what else could affect frequency? We tried to convince ourselves that amplitude was the culprit, but we were wrong. The higher the amplitude, the more torque necessary to return our pendulum to its equilibrium position. That left only one culprit in our eyes. We determined then and there that simple pendulum motion frequency and period rely solely upon length. We also chalked up our somewhat questionable discrepancy to inadequate measurements. We should have measured to 3 or 4 sig figs instead of 2. In conclusion, weight has little apparent effect in regard to frequency when dealing with simple pendulum motion, and simple pendulum motion can be measured using simple harmonic motion devices, but only to a small degree.